Hi, this is Mathman. I realized the video I made a little earlier on how to make or find a derivative wasn't so intuitive. It wasn't so easy to follow, so I thought I'd give it another go. Also, I did it a second time, and unfortunately, I screwed up technically and didn't capture my second explanation. So this is really the third time I've done this. Um, at least I have a little time, but I am. Um, I really screwed up because I thought I did a pretty decent job in the second time around. So I'm a little upset about that. But anyway, why don't we get to it and basically show you how to come up with a derivative. Now, don't pay too much attention at the complexity of this visual here. What we're going to do is we're going to take a look at this from we got a point P. Erase this, unfortunately. Okay, we have a point P, and we have a point, and we're looking at this curve. Now, the curve that we're looking at is y equals x squared, okay? That's what this curve represents. And we have a point P, x, y. We'll call it x1, y1 for now. And we have an x2, y2 for now. And remember, with a line, to calculate the slope of a line, we have the equation of a line, y equals mx plus b, where m is the slope, which is basically the change in y over the change in x. So if we look at the change in y over the change in x, we have this right triangle. And we're interested in the direction of that line, that slope, how steep it is. And so we calculate this by looking at 2 points along the curve. We have x2. Oh boy, this thing is starting to go. x2, y2, and x1, y1. And so we can find our curve, our slope, by going y1 equals mx1 plus b, and y2 equals mx2 plus b. And so, knowing that our slope is equal to y2 minus y1 over x2 minus x1, we're taking the difference between these two equations. So y2 minus y1, 2 minus y1, is equal to m x2 minus x1, and the b's cancel out. B minus b is 0. And then we just divide this, and we have the slope. M equals y2 minus y1 over x2 over, or minus x2 minus x1. And it doesn't matter anywhere along the line, it's always going to be the same. The slope will always be the same. Well, we're going to, even though we know that on this curve, we can't do the same thing as with a line, but it's the best approximation that we have. Just a second, I'm going to have to take this phone call here. Oh, sorry about that little break. I had a call. Okay, because we don't have any other better way for a curve, let's say with the line, we can use that change in y over change in x. Well, we don't have anything better to do with a curve that changes as we move along it. So if we look at the slope or tangent at this point, it's different than the tangent at that point. And you can see that as this curve changes, so does the tangent. So the best thing that we have is, the only tool that we have is to take a look at 2 points along the curve. We got a point 1, point 2. We're going to call that x1, y1, and x2, y2. And we're going to do the same thing as we did with a line, delta x, or delta y over delta x. But we see that the slope that we get here for this particular point, let's say this point P, that's P, is not exact. You can see that the slope of our approximation is not the same as the slope at that point P. This is P. So one thing we do notice is that if we start out with this initial approximation, and if we shrink our base, our delta x, we're going to notice that our delta y changes too. So if we make x smaller, then y is smaller. And so our slope changes as we change our x. So as delta x goes to 0 or gets smaller, the slope, you can see here, the slope lines change to become, when delta x goes to 0, the slope goes exactly to the tangent t. And that's what this shows here. We can see the green lines. Those are the different slopes of the triangles that approximate our slope at the point P as we squeeze our delta x in towards P as delta x goes to 0. And so what we're interested in then is to find the equation that gives us the slope here, and then squeeze delta x to 0 by taking a limit and seeing what results as we look at that slope. What happens to that slope? And it turns out that when we take that limit and we make delta x go to 0, we find that the slope becomes exactly the tangent point at the point we're interested in, and that's the derivative of the function at that point. So now we're talking calculus. So what is our slope here? So we go m equals y2 minus y1 over x2 over x, or minus x1. Well, here we're not dealing with any specific x's and y's, so we're going to be looking at x and y here, and this one at point P. This we can continue our dots here, and point P or Q, our x is x plus delta x, and y plus delta y. Those are our two coordinates. So that's y2, and this is y1, and that's x2, and that's x1. So, but remember, y equals x squared. So, when we're looking at the value for y2, we substitute for x in that. So y2 is equal to x plus delta x squared minus y1, which is x squared. Okay, and then down here, substituting x2, that's x plus delta x minus x. Now we have our slope, okay, our expression for a slope. And remember, our slope is delta y divided by delta x. So now we have an equation that represents the slope. And if we squeeze delta x to 0, then in our limit, we look at the behavior of this function, and we call that the derivative. So let's expand that out. We have delta y over delta x is equal to x squared plus 2x delta x plus delta x squared minus x squared. You see, I just expanded that expression, x plus delta x squared. Okay, so that's what that is. And now the denominator is x plus delta x minus x. So those x's cancel, and these x's cancel, and we're left with 2x delta x plus delta x squared over delta x. But then we see that these can cancel out, so we're left with 2x plus delta x. And that's what that is. So when we take the limit is delta x, right there, goes to 0, of delta y over delta x. We're taking the limit, really, of this function, 2x plus delta x. And that happens to be, when delta x goes to 0, 2x. And that's our derivative. And because we didn't do it at any specific number or place along the curve, this is a generalization of the tangent for this function at any point along the curve. So we now have developed or derived the derivative of y equals x squared. So now we have a function f of x y equals f of x equals x squared. Y prime, the derivative, is equal to f prime of x equals 2x. And this is the derivative. Okay, it's also the tangent of the curve at a given point. So let's take a look at, let's say x is 4. Then y is 16, because 4 squared is 16. And y prime would be 2 times 4, that's 8. So the slope or the tangent at 16 is 8, or at x equals 4 and y equals 16. So if this was 8 here, let's say that was 8, and this, let's say this was 4, let's say that was 4, and this up here was 16, right there at that point, then the tangent line at that point would be 8. That's the slope. And we can find that anywhere. We can find the slope of the curve anywhere along the curve because we have a generalized function. For example, if x equals 9, x equals 9, then y equals 81, and y prime, the slope or tangent at x equals 9, is 2 times 9 is 18. So it becomes steeper. We can see that the slope is becoming increasingly steep. So for our function y equals x squared, we have a derivative there. And we can do this for any polynomial, let's say y, let's put this up here. This was y equals x squared. Let's say we have y equals 3x to the third minus 2x plus 8. All right. What is y prime? Y prime, or the derivative of that. Well, we can go through the same thing. We can go delta y over delta x equals y2 minus y1. So this is 3x plus delta x cubed minus 2x plus delta x squared plus 8 minus 3x squared minus 2x plus 8 over, and that's the whole expression, minus, again, we would have x plus delta x minus x. So that's delta x. And when we work out the math, expand these, subtract that off from the expansion, we're going to be left, when we take the limit, as delta x goes to 0, of delta y over delta x is going to be, in this case, 9x squared minus 2. The derivative of any constant, if we have a function where f of x equals a constant, the derivative of f of x is 0. There is no derivative of a constant. The derivative of a constant is 0. And we could prove it by going through this whole rigmarole. You can do it yourself to prove it to yourself. But that's the case. The derivative of a constant is 0. So this is what we find for that function. So the derivative of this function we know now is 9. Whoops. Why this thing's hard to get right. 9x squared minus 2. And basically what we find for polynomials in general is if we have a function f of x equals a x to the n plus b x to the n minus 1 plus c. You can go on in any way. F prime of x, and you can prove this to yourself by taking a number of functions and taking their limits and seeing what results. You'll find that this formula works. A to the n times x to the n minus 1 plus b n minus 1 x to the n minus 2. And if you want to take the next derivative, f double prime is just the derivative of the derivative. So we end up with a times n minus 1 times x to the n minus 2 plus b to the times n minus 1 times n minus 2 x to the n minus 3, and so on. Usually we don't need to go beyond the second derivative. If a function is large enough, you can take second, third, fourth derivatives. They're usually not so helpful. The first one is helpful. It's the rate of change of the function at any given point. And we know that to be the tangent, so the f prime of x is the tangent of the slope of the curve at any given point, but it's also the rate of change of the curve at that given point. So it's also the instantaneous velocity of the curve at a given point. So tangent at a point or velocity at a point are two equal ways of looking at the derivative of a curve at a given point. Now, second derivative is the rate of change of the velocity. And the rate of change of the velocity, if you've ever been in a car and you're driving along in a car at 70 miles an hour on the highway, the only way that you know that you're moving is by watching the world around you pass by. But when you want to pass the car in front of you and you punch the gas pedal to the floor, you get thrown back in your seat. And you actually go faster, and that is called acceleration. Or let's say the car in front of you stops unexpectedly and you hit your brakes and you get lunged forward in your seat. And you should be wearing your seatbelt. The seatbelt holds you from getting injured by hitting your head on the windshield or on the steering wheel. That's also an acceleration, but in the opposite direction. That's called deceleration. But acceleration, deceleration, they're always a second derivative. They are the rate of change of the velocity of the curve. So very useful concepts here for us, because now we can use these. This is actually phenomenal. We can use these for physical systems, describing physical systems, because most physical systems are dynamic, they're moving, and we can use mathematics to express their distance. We can use mathematics to express their velocity. We can use mathematics to express their acceleration. So, for example, in rocket science, we use all of these because we want to know if we have enough velocity to put the rocket into orbit around the Earth, and what acceleration we need to get there, and so on. So that is basically how we've worked out or derived a derivative. So I hope this has been a useful and helpful insight. Again, it's not as difficult as people really make it out to be. There's mathematicians tend to emphasize certain things, like the function must be continuous and defined on its domain, and all kinds of fancy terminology that even Newton would have questioned, because he wasn't thinking in those terms when he invented the calculus, or discovered it, really. Worked it through logically in his mind. He didn't have all of those ideas, which are valid ideas, but they all arose many, many years after the first peoples were using calculus. Gottfried Leibniz and Newton were contemporaries, and they were both given credit for coming up with calculus at about the same time. Now, what mathematicians don't tell you is that calculus didn't have a firm or solid theoretical basis until Bernhard Riemann. He was a student of Carl Gauss. He was a student of Gauss. He also was a brilliant mathematician in his own right. He was the one that derived the fundamental theorem of calculus in the 1860s. So it was a long time after Newton that there was a firm theoretical basis for calculus, and it was Bernhard Riemann. He's also the author of one of the millennial problems they call the Riemann Hypothesis. You would have heard about it, at least in the movie A Beautiful Mind, and so you would have at least heard of, you wouldn't have gotten much in the way of an explanation of the Riemann hypothesis in that movie. And it wasn't until 1967, because Riemann used limits to prove, and much in the way that we are now, to show the validity, used limits to show the validity. But the idea that Newton used was he called fluxions, or infinitesimals. And there was a lot of criticism about these fluxions, these ideas that Newton used to derive the concepts of calculus. They turned out to be equivalent, but they didn't know that until 1967 when somebody proved that Newton's ideas were valid. So mathematicians don't tell you that it was a long time before calculus had any theoretical validity. So I think that does students a bit of injustice because you assume that Newton had everything all worked out in his mind. No, it wasn't. He was using it, and mathematicians were using it, and engineers were using calculus up until the 1860s, but they didn't have a theoretical basis until Riemann. And Newton's way of thinking wasn't proven until 1967. So this is 1860s, and this is 1967. And if students knew this, they wouldn't feel so bad that they're struggling with these concepts because it took the mathematicians a long time to put the calculus on a firm theoretical basis. So I just wanted to throw that in there because I think math is intimidating enough, and I think mathematicians can make it overly intimidating. That you have to be some sort of brainiac in order to understand it. It's kind of like a marathon runner. There are not too many Kenyans in this world. They're not. If you expect that you want to run a marathon, you're not going to do it in 2 hours. But if you work and you work hard, you're going to be able to finish it. Maybe it's 4 hours, maybe it's 5 hours, maybe it's 3 hours. But you're going to be able to finish it. Most people can do a marathon if they want. They may not do it in record time. I think the same is true with mathematics. I think a lot of people are intimidated away from understanding it, and it's really not as intimidating or bad as it may seem. So anyway, we're going to look at the power of calculus. We're going to take the look at the power of calculus in the next video. We're going to take a look at what you can do with derivatives. Remember those Taylor series that I gave you, where e to the x equals a naught plus a1x plus a 2x squared plus blah blah blah, goes on infinitely. Now we're going to be able to work out, instead of just giving you a Taylor series for that, you're going to be able to work it out for yourself. So you can find that this is a very, very, very powerful tool because Taylor series allows us, when you're able to transform functions into other functions, you gain insight into what those other functions, some of the properties and characteristics that are hidden or embedded within that may not be dislodged unless you have another way of looking at them. Also, we think that we were drawing different curves when we were looking at the sine and the cosine functions. Now we're going to be able to use calculus to actually fill in gaps that we were leaving out not that we were purposely leaving them out, but we didn't. We're just making an assumption that when we have this series of points, that they interconnect smoothly like that, instead of going like this. And so we're going to be able to use calculus to show that the behavior of the function is exactly the way we thought it should be. So calculus derivatives allow us to understand that. We're going to look at the power of calculus to help us plot big functions like x to the fifth plus x to the fourth, b, a plus c, x to the, let's say, second power minus d, something like that. That's a complicated function. Well, now we're going to be able to plot a function like that using calculus without having to resort to trying to create a big long table of x and y's and trying to calculate them out, and then maybe missing some behavior, because some of these functions make funky curves. Not that this, something like that. And if I missed some points, I may just accidentally draw it like this, and then I've missed this point here. So calculus allows us to find all of the points at which the curve makes changes. And they call them inflection points. So where a curve changes, okay, so we're going up there, we're going down here, that point at which the curve changes from up to down, that's called the inflection point, or down to up, that's an inflection point. And we're going to be able to use calculus to find these inflection points. I had already mentioned that in physics, calculus is equivalent to velocity and acceleration, and so calculus really is a mind-blowing and a mathematics that opens up a lot of possibilities for us. It's an amazing branch of mathematics that is open to us, to allow us to understand physical behavior and a lot of other things. And just the fact that it's fun in its own right. So anyway, I guess you probably haven't heard by now, but math is fun. And that's why Theoni Pappas wrote the book Joy of Mathematics, and it's a fantastic book. And we're gonna, after we take a look at the traditional calculuses, derivatives and integrals and getting areas and figuring out volumes and stuff like that. We're going to start looking at some of these things that Theoni Pappas has put in her books because they're just fantastic. We're also going to take a look at Fibonacci numbers, just things that we're going to look at down the road. I'm going to try to make this site as fun as possible, but I also think it's important to understand the fundamental basic mathematics that you need for college, for school, because it's meaningful. It is useful. We may even look at a degree of statistics, because statistics are very important, especially in the work environment. Statistical analysis is very important. So we're going to take a look at all that stuff. So anyway, I'm talking too long, but this is Math Man wishing you well. Stay in during this corona crisis. Please don't spread it. This is a scary, very scary disease, especially for old timers like me. The mortality rate is very high, and On top of that, some of us older people have underlying conditions that complicate it even more. Heart disease, lung disease, and so on. I'm hoping to retire someday, and I want to retire. I don't want to expire before I retire. I should make that a slogan. I don't want to expire before I retire. Sound a little like Muhammad Ali. Float like a butterfly, sting like a bee. I guess maybe you are all too young to remember that. When he fought Sonny Liston back in 1964, I believe it was. But anyway, this is Math Man, wishing you all the very best.